In section 4.5, we'll be looking at exponential and logarithmic equations. In particular, we'll solve exponential equations, solve logarithmic equations, and use exponential and logarithmic equations in applications. So first off is the idea that if b, x, and y are real numbers with b greater than 0 and b is not equal to 1, then if you have an equation that is b to the x is equal to b to the y, then the x and the y must be equal. So in other words, if you have an exponential equation where the bases on both sides are the same, then that forces the exponents to be the same. This results from the fact that y equals b to the x is an exponential equation, and all exponential equations are 1 to 1. So whatever the exponents is on one side must be the same exponent on the other side. Let's look at example 1. Solve. 2 to the 3x minus 1 is equal to 32. So the trick here is to make the bases the same. Let's start with 2 raised to the 3x minus 1 power. 32 is actually 2 to the 5th power. And now that the bases are the same, they're both 2's, then we know that the exponents must be equal. So 3x minus 1 is equal to 5. Move the 1 over, get 3x is equal to 6, and x is equal to 2. So the solution to this equation is x equals 2. Let's look at example B. 16 to the 1 minus 2t power is equal to 1/4 to the t. Both of these numbers, 16 and 1/4, live in the 4 family. So 16 is really 4 squared. And then we have the other exponent, 1 minus 2t. 1/4 is actually 4 to the negative 1 power. If you recall, the power of negative 1 is a reciprocal. So we get 4 to the negative 1 to the t power. Now recall that we have this property of exponents. If you have a raised to the x, and then all of that is raised to the y, that is the same thing as just multiplying the exponents together, and you get a to the x times y. We'll use that property on both of these. So we get 4 raised to the 2 times 1 minus 2t, and that's equal to 4 raised to the negative t power. Since the bases are now the same, then the exponents must be the same. So we get 2 times 1 minus 2t is equal to negative t. Distribute the 2. We get 2 minus 4t is equal to negative t. Move the t over, we get 3t. Move the 2 over, we get negative 2. Divide both sides by negative 3, and we get t is equal to negative 2. So the solution is the quantity t equals 2/3. Let's look at example C. We have 5 to the x is equal to 12. Notice that 5 and 12 are not in the same base family. So in this problem, let's go ahead and use logarithms. We're going to take the natural log of both sides. So we get natural log of 5 to the x is equal to natural log of 12. Now recall we have this rule that says you can take the exponent on the argument and bring it down in front and multiply. So we're going to get x times natural log of 5 is equal to the natural log of 12. Divide both sides by this natural log of 5. That's one single number. So we get natural log of 12 divided by the natural log of 5. And that is an exact answer. Now notice that that's also equal to log base 5 of 12. That comes from the base changing formula, where if you're taking the division of two logs that are in the same base, then the bottom argument can serve as the new base of a log, and the top argument serves as the argument for the new log. Now, if you type in the natural log of 12 divided by natural log of 5 in your calculator, you'll get the decimal version, 1.544. Let's take a look at page 2. Recall that the log in base b of b to the x is equal to x. That's one of the properties that we had from our previous lessons. Example 2, solve for x using logs. So we have 5 times e to the 2x minus 1 minus 9 equals 30. So to solve this, I'm going to try to get the e to that exponent by itself. So let me rewrite the equation. And to solve this, let's move the 9 over. We get 5 e to the 2x minus 1 is equal to 39. I need to get rid of the 5 in front, so divide both sides by 5. Now we have e to a power is equal to 39 over 5. Here we're going to take the log. And the log that we choose, it's usually best, if you can do this, it's usually best to take the log in the same base as the base of the exponent. Since the base of this exponent is base e, we're going to take the log in base e, which is natural log. Then we're going to use that property from above, and essentially the natural log and then e to a power gives us just whatever that power is. That is what that property is saying. This is because the natural log and e are inverses of each other. And then we keep going and solve this equation. We're going to move the 1 to the right. Now we can't add that into the natural log, so we're going to use parentheses there, and then add 1, and then divide everything by 2. So we get x is equal to the natural log of 39 over 5 plus 1 divided by 2. Let's look at example 3. Solve for x using logarithms. So let me rewrite the equation. It's 10 to the 8x minus 3 plus 4,500 is equal to 24,000. Let's start by moving the 4,500 to the other side. Subtracting that from 24,000 leaves me with 19,500. Again, we want to take the log of both sides. Since the exponent is in base 10, we'll take the log in base 10, which is common log. The common log of 10 raised to the 8x minus 3 is just 8x minus 3. And then we continue to solve for x. Move the 3 to the right side. And then divide by 8. Let's look at example 4. Example 4 says solve for x. 7 raised to the 3x minus 1 is equal to 4 raised to the 2x plus 5. Here, the 7 and the 4 are not in the same base family, so let's use logs. Now, you could use the log in base 7 or the log in base 4, but since those are not going to work together anyway, you might as well use an easier log, and that easiest log to use is natural log. So I'm going to take the natural log of both sides. Next, bring the powers down. Now, notice that the power here is binomial, so there's two terms. I need to make sure that the natural log of 7 gets multiplied by both the 3x and the 1. So I'm going to use parentheses around that. Let's do the same thing on the right side. And use parentheses around that 2x plus 5 as well. Next, distribute the natural log of 7. So we're going to get 3 natural log of 7 times x minus the natural log of 7 is equal to 2 natural log of 4 times x plus 5 natural log of 4. Now, to continue solving, anything with an x gets moved to the left, anything without an x gets moved to the right. So 3 ln 7 times x is on the left. We're going to move the 2 ln of 4x to the left side. So that's 2 ln of 4 times x. On the other side of the equation, let's move the natural log of 7, and we already have 5 ln of 4. Next, let's factor out the x from the left side. That leaves me with 3 ln 7 minus 2 ln 4. The right side stays the same. And then finally, divide by the coefficient. So we get ln of 7 plus 5 ln of 4 divided by 3 ln of 7 minus 2 ln of 4. Let's look at example 5. Solve for x. 2x times e to the x minus 6 e to the x is equal to 0. So let me rewrite the equation. Oops. Now notice that both terms have e to the x, so I'm going to factor that out. So that's 2x minus 6 equals 0. And then, once it's factored, split it up and set each factor equal to 0. Let me solve the one on the right first. Move the 6 over, gives me 2x equals 6 and x equals 3. The right side, we're asked to find the solution for e to the x is equal to 0. Recall from the graph of y equals e to the x that e to the x has a horizontal asymptote at 0, and in fact it is never equal to 0. So the equation e to the x equals 0 has no solution. So you don't get a contribution from e to the x equals 0. So the only solution is x equals 3, and you can write that as a set 3. Let's look at example 6. Solve for x. E to the 2x minus 8e to the x minus 20 equals 0. So first, note that e to the x squared is the same thing as e to the 2x. So this tells me that we could rewrite the original equation as e to the x squared minus 8e to the x minus 20 equals 0. And now it looks like a quadratic. We have a term that's squared, we have the term in the middle, and then we have the constant on the end. So we're going to factor this like a quadratic. But the question is, what do you put in the first spots? Instead of x's, we're going to put e to the x's. Verify that e to the x times e to the x is e to the x squared. It is. Then, what two numbers multiply to give you 20 and subtract to give you 8? Those numbers are 10 and 2. And we need a negative, so we're going to make the 10 negative and the 2 positive. Next, once it's factored, split it up, set it equal to 0, each factor. So we get e to the x plus 2 equals 0, and e to the x minus 10 equals 0. On the left side, we get e to the x equals negative 2, which cannot happen. Remember that e to the x can never be negative or 0, so there's no solution from there. On the right side, e to the x is equal to 10. If you take the natural log of both sides, you get x is equal to natural log of 10. So our only solution here is the natural log of 10. Next, let's look at logarithmic equations. Let b, x, and y be positive real numbers with b not equal to 1. Then log base b of x is equal to log base b of y. Implies that x is equal to y. So again, this comes from the fact that y equals log base b of x is 1 to 1. So whatever whenever there's the log in the same base, if those are equal, then the arguments must be equal, and the x is equal to y. Example 7. Solve for x. Log base 2 of 5x minus 3 is equal to log base 2 of 3x plus 11. Since we have two logs that are in the same base, then we know that the arguments are the same. And so we set those equal. 5x minus 3 is equal to 3x plus 11. Move the x's over, move the constant over, and we get x is equal to 7. On page 5, solve for x. Log base 3 of x is equal to 2 plus log base 3 of x minus 1. So to do this one, first I want to move the log from the right side to the left side. Then on the left side we have the difference of two logs, so I will combine them using division. So we get log base 3 of x over x minus 1 is equal to 2. Next I'm going to turn this back into exponential form. So we're going to get 3 squared is equal to x over x minus 1. 3 squared is 9, so that's 9 is equal to x over x minus 1. Let me cross multiply, get 9 times x minus 1 is equal to x. Distribute the 9, you get 9x minus 9 equals x. Moving the x's to the left, you get 8x. Moving the number to the right, you get 9. And then x is equal to 9 over 8. Now you need to be checking the answers for logs. You can sometimes generate an answer that does not work. And all you really need to check is that everything is valid. So log base 3 of 9 over 8 is equal to 2 plus log base 3 of 9 over 8 minus 1. You could do the log on the left and you could do the log on the right, so it will check out. Example 9, solve for x. Natural log of 4x minus 1 equals 5. So here I'm going to use this property. B to the log base b of x is equal to x. Is equal to x. So if you raise a base to the log base b of x, then the base and the log base b are inverses, so they cancel and they give you what the argument is. I'm going to use that trick here. We have a natural log of 4x minus 1, so I'm going to make that the exponent of e. So e raised to the natural log of 4x minus 1 is 4x minus 1. That equals e to the 5th. And then I'm just going to move the 1 over and then divide by 4. And so the solution is e to the 5th plus 1 divided by 4. Let's look at example 10. Bob invests $2,000 at 4% compounded monthly. How long will it take for the account to increase to $2,500? So first, recall the compound interest formula. A is equal to P times 1 plus R over N raised to the NT power. The future amount is $2,500. The present amount is $2,000. The rate is 0.04, and it's compounded monthly. What we don't know is the time t. When the exponent contains the variable, then that's when you want to use logs to solve for the variable. To get to that point first, though, we need to divide by 2,000 on both sides. 2,500 divided by 2,000 is 1.25. And that leaves me with 1 plus 0.04 divided by 12 raised to the 12t power. Now I can take the natural log of both sides, then we can take the exponent and bring it to the front. And then to finish this, I need to solve for t. So I'm going to divide by everything that is being multiplied by t, which is both the 12 and the natural log of 1 plus 0.04 over 12. And when you work that out, you get t is equal to 5.59.